like to introduce one more interference phenomenon, which shows up in the world of optics, and that is thin film interference. So to start, I'll just ask you to think about the last time you were in a parking lot shortly after a rainstorm. You probably saw some uh, little rainbow-ish kind of things on top of water puddles in the parking lot. And what was happening there was oil and gasoline that had dripped out from some of the cars was floating on top of the water. And it turns out that this very thin layer of oil or gasoline that you have on top is what's responsible for the pretty colors. So let's go ahead and get into how that works. But to start, I need to quote an experimental result known as Lloyds Mirror. I can't really discuss how the experiment works, but the result, it goes like this. Let's say that you had some light coming in, bouncing off of a surface. Now let's say that this material here was a lower index of refraction and this was a higher index of refraction. So we can think as an example that this is air and this is glass. What Lloyd was able to demonstrate is that we'll see that some of the light goes on through into the glass. That's called refraction. But for the bit that's reflected, what Lloyd was able to demonstrate was that what was reflected back was 180 degrees out of phase. So this is like an analogy to when we were talking about if I had a fixed boundary and I had a string and the pulse came in like this. When it reflected back the other way, it reflected back upside down. Exactly the same deal here. Effectively, the bit of the light wave that reflects back gets reflected back upside down. This bit here that gets transmitted through does not change phase. Now, if you have the reverse situation, so say you have a ray of light coming in like so, and here this is the higher index of refraction and this is the lower index of refraction. So think like that our ray of light is in glass and that this is air on the other side of this boundary. It turns out that neither the refracted nor the reflected ray change phase. So from the reflection part, the analogy in a mechanical wave was if you had a free boundary. So there we saw a pulse that came in right side up would reflect back out right side up. It's the same deal here. If say my electric field vector is pointing to the left here, when it reflects back right this spot, it'll also be pointing to the left. Whereas here, if it was pointing to the left, it'll be now pointing to the right, as an example. So if we go ahead and think, so the application here is what if we have a thin film on top of our glass, say on top of our glass as an example. So something like this. So we'll say that this index, this is N1. We'll say that this is a greater index than N1. And we'll say that this material here, index N3, is greater than N2. So this could be air, for instance. This could be glass. And this could be a very carefully chosen metallic coating. Some sort of metallic oxide. Or something like that. I'll just say coating. And the key bit here is this is going to be really thin, as in a reasonable, as in fractions, as in a few wavelengths of light. So we're talking maybe a few hundred molecules deep, a few thousand at most. So pretty thin as these things go. So in a situation like this, if light were to come in to this first surface, some of the light will get refracted through. And we saw that there will be no phase change there. But some of it will get reflected. And because this is a higher index than this, we'll have a phase change. Now, what about the light that went on through here, that got reflected here? This will also, because some of it will go on through, and some of it will get reflected back here as well. And because you're bouncing off a higher index, there will also be a phase change. Now, there will also be some rattling back and forth within the layer, but that is beyond the scope of this treatment and doesn't change the main outcome that we're looking at. So this is a case where where you had two phase changes. And I'm going to call this a case 1 situation. And there is another possibility that I would also classify as case 1. And that's the inverse. So let's say your exit. So if this was the entrance to a surface of a lens, or we had air, the coating, and glass, if we were to reverse this, so that, say, this index here was, sorry, I still need to call this N1, N2, N3. So here, N2 is less than N1, and N3 is less than N2. So that, let's say this is glass as an example. Our coating that's chosen to have an index of refraction in between the air and the recipe glass we're using. And then finally, the air. So this would be the bit where you have the light entering one surface of the lens. This would be exiting the other surface of the lens. Well, in this case here, the incident ray will have a bit that's transmitted through and a bit that's reflected, but there will be no phase change here because you're bouncing off a lower index. And similarly, this bit here, the bit that gets transmitted through, of course, has no phase change, but neither does the bit that's reflecting back. So again, no phase change. And I'm indicating phase changes with the dotted line here. So either of these are what I would call a case 1 situation. So if we say that the thickness of our film is T, if I want to maximize the amount of light that I'm reflecting off at a particular wavelength, that would be looking to get constructive interference. And here the deal is that the extra distance that this light traveled is this bit down and this bit back. Now this ray coming back here is going to interfere with the bit that reflected off of this surface here. If we're going to have this color reflect back brightly and have constructive interference, I need this total round trip distance, so 2t, because the thickness is t, but the round trip is 2t. I need this to be some integer number of wavelengths in this medium here. So this would be the wavelength in the vacuum. This is the index of our film. So the combination of these two is one wavelength in this medium here. As long as this round trip is an integer number of these, then this reflected ray here and this reflected ray here will be in phase with each other, and we'll have constructive interference. So this m here is just an integer. It's 1, 2, 3, 4, etc. I mean, 0 is a possibility. I guess I can put that in parentheses here, but it doesn't really count because then you'd have no film at all, right? So we'll get rid of that. Now, if I want destructive interference, so if I don't want the light to reflect back, but instead pass on through, which if you're designing a camera lens is exactly what you want. A pretty substantial chunk of light reflects backwards away from the sensor in a camera every time the light hits either surface of a lens. And at absolute minimum, in most camera designs, you tend to have at least 4 lenses. You can get down to 3, but 4 is a really typical number. And each lens has 2 surfaces, so that's 8 surfaces. If you allow light to reflect back at each of these 8 surfaces, only a small percentage, like on the order of 10% or so, will make it to the sensor, and that's an awful lot of lost light. So if I can make it so that the reflected light, when it comes back, will be 180 degrees out of phase with the light that reflected off the top of the coating, then there won't be any light reflecting back because it will have interfered out, and that forces the light to go on through, which is what we'll want there. So looking for destructive interference. In this case here, in order to have, say, a trough meet a crest, I need this round trip distance either to be half a wavelength, 1.5, 2.5, 3.5, something like that. So 2t equals m plus a half lambda over n, because again, it's the wavelength in this film right here. And now here, 0 is totally a possibility, because 0 plus a half is a half. All right. So the other possibility that you can have is what you actually have with the oil slick or the gasoline slick in the parking lot. So this is what I call case 2. And this is where you have exactly one phase change. So your possibilities here are either that the index of the material in the film is less than the surroundings, so N1, N2 less than N1, but N3 greater than N2, or the other possibility is if this is N1, you have N2 greater than N1 and N3 less than N2. So those are 2 possibilities. So in this example here, where N2 is less than N1, light that comes in, some of it will be transmitted through, and the bit that reflects back will have no phase change, which I'm indicating with the solid line. Then at the second surface, some of it will also transmit through, and some of it will reflect back, but it will change phase because it's bouncing off of the higher index. Here, we just reverse which surface is giving us the phase change. So here you'll have the ray coming in, we're bouncing off the higher index, so that's the one that changes phase. This transmits through, that, and then we'll have a transmitted bit there, but this bit reflecting back will not change phase. So, because only one of them is changing phase versus both of them. So, for instance, here, neither of them changed phase. Here, both of them changed phase. Same difference. The effect canceled out. Here, because only one of them changes phase, that does affect our constructive and destructive interference situation. So for constructive interference now, this time I need the half, 1.5, 2.5, whatever wavelengths in the film. And this is because, say, if I do a half a wave, I will be upside down. But then the fact that I inverted myself at this reflection undoes the effect of half of a wavelength round trip, or 1.5, 2.5, 3.5, whatever. And destructive, this is where you would have constructive interference, but for the fact that we changed the phase at one surface. So that will force you to have destructive. So you reverse the situation. And it turns out this case is what gives you the rainbow slick on the in the parking lot. So in the parking lot situation here, you have your water puddle. Index of refraction of water is 1.33. You then have the gasoline floating on top of the water, and the index of refraction of gasoline is right around about 1.40 usually. And then you have air. Index of refraction close enough to 1 for us. So when the light comes in, here we're bouncing off a higher index, so we'll have our phase change. This bit goes through, but the bit that bounces here will not have a phase change. So for constructive interference, where you see the pretty colors, that's going to be 2t equals m plus 1/2 lambda over n. Or if I want to rearrange this, I can get that the wavelength of the light is going to be 2nt over m plus 1/2. So the deal here is if you actually look at the puddle up close. So this is the water here. Your actual puddle of gasoline is probably going to look something more like this. Just a big bead on top, but it kind of lumps a bit. And so like this bit here will be thinner. And because that's thinner, that's going to force a lower wavelength. So something towards the blues or purples. On the other hand, say in here, this is thicker. Makes T bigger, means that in order to get constructive interference back, you'll have to have a longer wavelength. I should probably really say short here. So we'll have a longer wavelength, which this would be in the reds. And then if this gets thick enough, so then eventually this will head off, get long enough that it'll drop into the infrared, just like here it'll be thin enough that it falls off into the ultraviolet. But if this gets thick enough, then we get to a point where instead of having m equals 0, we can have a where thicknesses for which m equals 0 would work. We can then repeat the cycle with thicknesses where m equals 1 works, and then possibly even m equals 2. And so that's why sometimes you'll see the rainbows, those jaggy rainbows kind of repeat themselves when you look at those puddles. Alrighty, well that will do it here for interference. Have a good one.